All right, I'll begin with a word of prayer, guys. So, Heavenly Father, we thank you for this day. We thank you for your grace. Thank you that you love us even when we don't love you, Lord. And we just praise you for this opportunity we have just to meet together and to enjoy a little bit about your creation, Lord. We thank you for math. Just pray with us today. Help us in our understanding and just bless this class, Lord. In your name I pray. Amen. Okay, so dot products. What is a dot product? You have two vectors, right, A and B, and you can take their dot product. Now, let's just suppose that these are three-dimensional vectors for a second. So, in other words, I've got A1, A2, A3 dotted with B1, B2, B3. Right? So what's the definition? The definition is that the dot product is simply A1, B1 plus A2, B2 plus A3, B3. So the dot product of two vectors is a number, right? It's a scalar. It's not a vector again, right? Now this scalar has deep significance, deep geometric significance, as we'll talk about today. All right? We're still starting, so I should mention that another way of looking at this would have been, well, let me just, a little discussion here. Remember we had x hat is equal to 1, 0, 0. Y hat is equal to 0, 1, 0. And z hat is equal to 0, 0, 1, right? Let's see here. So how does a dot product work for these ones? Like, let's see here. For example, what's x hat dot x hat? 2x hat? No. So think about this. A1 and B1 are both equal to 1. A2, B2, A3, B3, these are all 0. So as I think about applying the definition, the only thing that survives is A1, B1, which is 1 times 1, which is 1. On the flip side, if I have x hat dot y hat, and if I have x hat dot z hat, those are both 0 because there is no matching component, right, which is both non-zero. Like there's either 0 in the A or there's 0 in the B. See that? So those dot products are 0. Likewise, y hat dot y hat is equal to 1, and the other two, y hat dot z hat is equal to 0. Let's see here, z hat dot z hat is equal to 1 also, because when you plug that up into this definition, you get 0 plus 0 plus 1 if you think about it. You're like, well, why didn't you write the other ones? Well, there's something else I know about the dot product which I haven't told you guys yet. It's commutative. All right, so notice this. If I change the orders of the A's and the B's, I have the same expression, right? Because real number multiplication commutes. So you can easily convince yourself that this is the same as B dot A. I'll prove that in a bit, but I'm saying it now just to point out I don't need to actually calculate y hat dot x hat here because I already know that y hat dot x hat is 0 because I know that x dot y hat is 0, right? So x dot y hat is equal to y hat dot x hat, and they're both 0. All right, so I'm just trying to collect together all of the dot products of these little unit vectors. So what I'd like to point out to you is we could also look at the dot product in terms of just these. Let me put them in a green box here. Sometimes another way of thinking about the dot product is you could take these as like the fundamental truth, and you could just assume the dot product sort of works in the intuitive way, right? So like if I have A dot b, that would be a1 x hat plus a2 y hat plus a3 z hat. And if I take the dot product with b1 x hat plus b2 y hat plus b3 z hat, right? Then whatever this dot product is, it should be obey usual distributive laws. If that's the case, then this works out to what? Like a1 b1 x hat dot x hat plus a2 b2 y hat dot y hat, right? Plus a3 b3 z hat dot z hat plus other stuff, right? But all that other stuff has dot products of either x hat and y hat, x hat and z hat, or y hat and z hat. All of those things are 0. And all of these things are 1, and there you go. That's back to this again. So all I'm trying to tell you here is there's different ways you could actually calculate this thing, as opposed to actually just going back to that fundamental definition. You could remember the things I've boxed in green and sort of just do algebra. It's another way you could approach the calculation. Sometimes it's useful to do it that way. Okay. Sorry, I was kind of chasing a rabbit right there. Let me go back on the straight and narrow and tell you properties of the dot product. All right? So what are important properties of the dot product? So a dot b is equal to what? What's one of the fundamental things here is it's symmetric. Or well, I should say it's commutative. All right, a dot b is equal to what? B dot A. All right, I'm going to submit to my notes. It'll make me behave. Sorry, I'm still kind of giddy after business calculus. Let's see here. A dot b is equal to B dot A. Another thing which I just used, but you can prove, and we don't prove everything in here, but we will do some proofs. I want you to be able to give an account for those things that you believe. So it distributes across addition that way. It distributes across addition the other way as well. Of course, that's not surprising, because if you've got that commutative property, you could get the third thing I'm writing from the second thing I wrote. Scalars factor out. So if I've got scalar multiplication, I can pull the scalar out like that. And okay, so it's 1, 2, 3, 4, 5. It's non-negative. A dot A is greater than or equal to 0. But more than that, when can it be 0? The dot product of a vector with itself. It's 0 when, and when what? Yeah, only for the 0 vector. Only if A is equal to 0 itself. Now, how would you prove these things? I won't prove all of them, but I want to give you a flavor of how you could prove some of them, okay? So the first thing I would do before I tried to prove anything is I try to come up with a better definition than the one we've given. And I'm greedy, so I don't want to prove it in 3 dimensions. I want to prove it in n dimensions. I mean, why not? So what's the dot product in n dimensions? Here's the formula. A dot b is equal to a sum. You remember those? Don't worry, I'm not putting infinity, I'm putting n. See, it's harmless. There's no convergence and divergence. It's just adding n things together. It's harmless. Honestly, folks, that part of Calculus 2 where you study convergence and divergence, that's way more sophisticated than anything I'll do this semester. And there's really no reason that should be in the introductory calculus sequence, logically speaking. I mean, I know it's there, but to me it's just so much more sophisticated than anything else we do. I think it's a holdover from a previous time. Anyway, so there's a nice definition. So if I want to prove commutativity, for example, it's as simple as this. Okay, so properties of real numbers. AI times bj is equal to bj times ai, right? AI and bj, those are just real numbers. They commute, right? But what's that? That's exactly b dot a. Which is the same thing I said over here, but I didn't write out. To actually write that out over here, I'd have to have another step. b1a1 plus b2a2 plus b3a3. So there is the full proof in the no summation because I'm afraid of sums way of proving it, okay? Fortunately for you guys, I am not afraid of sums. In fact, I embrace them for questions like these. Okay, so for like 3, how would you prove that? A dot b plus c. So that's the sum over I of ai times b plus c I. Oh, I seem to have put a j there somehow. How'd that happen? I've got a j. There is an easy way to fix this. They're all j's. J is a good letter. Okay. OJ? One person got it, good. The rest of you were like, no, I am not going to acknowledge what just happened. It's good. Some of you are still confused what I'm talking about. Also fine. How do we add vectors component-wise, right? So this is nothing more than bj plus cj, right? And so what I have here is I have a sum of aj, bj plus cj, plus aj times cj. But by properties of finite sums, the sum of sums is the sum of sums. I know it sounded like I didn't say anything, but I'm writing something. Keep wanting to go back to I. Sorry, I question the wisdom of writing this out today, but I'm too far in. Okay, so this is a dot b plus a dot c, and there you have it. So you can prove these things with arguments like this. I mean, and you'll save a lot of writing. And this is just the reason I'm showing you. I mean, these are not so hard that you couldn't do it this way, right? But once we get into some deeper things, knowing the summation notation for dot products and later cross products is actually very, very useful. Okay, now let me get back to something more interesting. These are the properties of dot products. Know them, love them, use them, all right? This, 5 and 6, are really important, and I will remind you, let's take you back all the way to yesterday. It was so long ago. I know. I hope you guys don't get tired of me because you'll see me every day. Let's see here. So what did we talk about at the end of last class? You guys remember? Yeah, the distance from the origin, and then we argued if we took 2 points in R3, we could look at the vector which connect the directed line segment connecting those 2 points, or the vector connecting those 2 points, and we said, well, the length of that vector should be the distance between those points. Or I guess we said the distance between those points should also be the length of the vector. But however you want to slice it, we basically discovered this formula yesterday, which is that the length of A, right, should be the square root of what? Say a1 squared plus a2 squared plus, let me just do it for n dimensions since it's about the same trouble. Again, we're primarily interested in either 2 or 3, but you know, that's the length of the vector A, right? That's its so-called magnitude. How can I write that in terms of a dot product then? Do you recognize? What if I rewrote this one more step? Maybe you'll see it. It's obvious if I write it this way. A1, plus A2, A2, right? AN. A smarter professor would have done this for 2 dimensions. Save me some writing. What is that? Yeah. The square root, and when you say the vector multiplied by itself, what do you mean by that? Exactly, yeah. Now, I say multiply by itself. It becomes important. There's no ambiguity right now, because we only know a dot product, right? But very soon we'll learn a cross product, and then we'll have 2 different ways to multiply vectors, right? And they will be very, very different, these 2 different ways. The dot product gives us a number. The cross product we're going to learn gives us a vector, all right? So here is one of the significant aspects of the dot product. It tells us how to calculate the length of a vector, its magnitude. There it is. Here's an application of this way of thinking. I think I told you, well, I don't know if I told you or not. I did this in some other class, so it may not be the case that I've talked about in here. If you have a scalar multiple of a vector, how does the magnitude of a scalar multiple relate to the magnitude of the vector? Like 3 times a vector. How long is it compared to the vector? Let's call the vector Bob. If I take Bob and I multiply him by 3, how long is 3 Bob? Like your question is too simple. I refuse to answer it. It's 3 Bobs. The length is 3 Bobs, right? If I take the vector and if I multiply Bob by minus 3, right? I have 3 Bobs in the other direction, but the magnitude, the length of it is still 3, right? So if you think about that, the rule is that scalar multiple of a vector is going to be the absolute value of the scalar multiple times the length of the vector, right? So we can derive that really easy from this formula, right? Because CA, square root of CA dot CA. But remember, scalars factor out of the dot product, which I stated and haven't proved, but you can see how to prove it. I'm not going to prove everything because, come on, you don't want to see it either. And so properties of the square root, that's the square root of C squared and the square root of A dot A, right? What is the square root of C squared? No, it is not. It is plus or minus C, right? If C is negative, it's minus C. Yes, in fact, this is a formula for the absolute value of C. If you want to, people are like absolute, goodness gracious, 126 students got X on my brain. Oh, I tell you. I mean, so sometimes you'll see people define the absolute value function like this. If I want to define the absolute value function, I just say this. It says the same. Yes. And you can differentiate it without breaking into cases. Want to see? I don't know. I can make up some really horrible calculus 1 problems on the basis of this hidden knowledge. But anyway, don't worry. You guys are safe. You're in calculus 3. I can't get you there. I'm not even teaching it this year. You're safe. Oh. But we do calculus in here, don't we? Anyway, so no one in their right mind puts tricky calculus 1 and calculus 2 and calculus 3. You guys have enough trouble figuring out the vectors. Why add insult to the injury, as the saying goes? All right. Sorry. I will behave and move along here. So the one answer to, well, what's the dot product? What does it mean? It tells me something about the length of a vector, right? You're like, okay, well, that's nice, but what is A dot B? What is A dot B geometrically? Like, what is the meaning of the dot product? Why are we looking at this thing? That's a good question. All right, we're going to get to that. But first, I must tell you some more properties. These ones are not so easy to prove. Oh, actually, one of them is. I already just proved it. Sorry. Oops. Well, okay, good. Proved. 2, so-called triangle inequality. The length, oh, I'm sorry. These are not properties of the dot product as much as they're properties of what? Yeah. But as you can see, there's a connection between magnitude of vectors and the dot product. Now here's one that actually connects the dot product and the magnitude specifically. This is the really important one. This is absolute value I'm writing here. Okay, the absolute value of A dot B, okay, is less than or equal to the magnitude of A times the magnitude of B. Oh, and okay, so for the length of A is greater than or equal to 0, and 5, the magnitude of A is equal to 0 if and only if what? Right, a vector has 0 length only when it's the 0 vector, right? If somebody tells you that they have a vector which has length 0 and it's not the 0 vector, they're playing fast and loose with the meaning of length. And they're probably a physicist. Now, number 3 has a name, so we like name calling in here. What do you want to call it? Actually, it's not up for grabs. It's the Cauchy Schwarz inequality. Hopefully I'm not misspelling Schwarz. There's 2 Schwarzes. I know how to fix this. Cauchy Schwarz inequality. All right, we're safe. That one's not so easy to prove. But that actually really tells you geometrically. That's so crucial in terms of understanding what the dot product really is. Because what does the Cauchy Schwarz inequality say about the following fraction? Anyway, I'm not going to prove these. The proof is in my notes. I'll let you read it. I've proved enough already today. Okay, so let's move along here. I want to talk though, so I'll let you read the proof for these things. I'm going to move along here. So let's have a discussion though. So you guys tell me, if you think about the fraction A dot B divided by the length of A times the length of B, what can you say about that fraction? Yeah. Less than or equal to 1. Now, can you see why he says that? So you're like, you take the Cauchy Schwarz inequality, right? Now, I guess to be fair, let me put some absolute values here so that you can be exactly right, okay? Otherwise, I would have to say it's less than 1, but it's larger than minus 1. But you're probably thinking this being here and just dividing, right? You divide both sides of this. Oh, wait a minute. When can we divide both sides? What do we need to make that division? Yeah, the vector better not be 0. We learned from 5, the magnitude is not 0 if the vectors are not 0, right? So for A and B non-zero, certainly this is less than or equal to 1. But by the way, by 4, I could just as well write these absolute value bars on the whole thing because the denominator is also a positive quantity, right? So I can pull that inside the absolute value. Do you guys remember how to work with absolute values? What does it mean if I have absolute value of x less than 3? What's that say if I unfoil it? I mean, if I unwrap it as 2 inequalities, what is it? Right, minus 3 less than x less than 3, right? this says that the distance of x from the origin is less than 3 in terms of the number line. So if I unravel this, what this really says is that minus 1 is less than or equal to a dot b divided by the length of a, length of b, less than or equal to 1. Well, this is some quantity which has values between minus 1 and 1 inclusive. I reckon this could be a cosine or a sine. And so this motivates us to define this as being the cosine of the angle between the vectors. Right? Now you're like, well, so anything between minus 1 and 1 can be a cosine or a sine? I can assign a cosine and a sine of an angle to it, right? That's just analysis. But there's a more deep geometric question to ask. You said it's cosine of the angle between the vectors. Does that match my geometric understanding of the angle between the vectors? Right? That question is still open in terms of what I've written on the board. But let's just make a proposal that a dot b is equal to magnitude of a, magnitude of b, times the cosine of the angle between them. What I'm saying is that this is an implicit definition of theta. All right, and by our custom, we'll take theta to be between 0 and pi. All right. Now, so I would say, so how do you make a connection between this and the geometric notion of angle? Like, what would you have to do that? I guess you got to draw some pictures, right? So that's what I do in the notes. I look at, and it took me some time to think this out. Actually, I don't want to do this in class. I'll just let you read it. But on page 25, that whole discussion there, I introduced theta tilde, which is the geometric angle, and I show that theta is equal to theta tilde by looking at a triangle in space and showing that this angle, algebraically defined, matches geometrically what you would define to be the angle between the vectors. So you can look at that if you want. But just trust me, if you want to do that in fact this is, honest to goodness, the angle between A and B. All right, so now there's nothing three-dimensional about this discussion. This just as well defines the angle between vectors in 5-dimensional space or 10-dimensional space or 2-dimensional space, which is kind of cool because I can't directly visualize vectors in 10-dimensional space. I don't know about you, but I could calculate the angle between them. Wouldn't be that hard. All right, let me show you guys a standard example that if you had physics with me, you're not allowed to answer this. So here's a question for you. What is the angle? Suppose you have a cube. Here's my cube, right? And I want to think about, I'm going to put the back corner of it on the origin, right? And my question basically is just this. What's the angle between this vector, let's call it A, and this vector, let's call it B? So B is the vector that goes from the origin out to the opposite corner, and A is just the vertical leg. What's the angle between A and B? So let me take a guess. 45. That's my preferred guess. Let's calculate it. So let's without loss of generality, you can give the cube any size you like. Let's just let it be the unit cube. So that means that B is equal to, what is it equal to? It's equal to 111, I think. And A is equal to 0, 0, 1. So if I calculate the length of A, what is it? What's the length of B? Square root of 3, right? What's A dot B? It's, let's see here, to do the dot product, 0 times 1 plus 0 times 1 plus 1 times 1, it's equal to 1. So cosine of theta then, by definition essentially, And again, I'm saying you could justify. For us, this is the definition of theta, all right? I will admit, if you're geometrically minded, you're like, you haven't addressed the geometric question. Fine, I haven't. It's in my notes on page 25. Cosine theta then would be equal to what? It would be equal to a dot b, which was 1, divided by what? Square root of 3. Now you can take the inverse cosine to get 54.76 degrees. Am I right? Oh, gosh. Was it 56? 54? Okay. As you can see, yeah, well, I do this every year in physics, or I used to. Well, the point is you can trick yourself in 3 dimensions, just drawing pictures on paper, right? Or boards. Because you want it to be 45 degrees, because you want that center slice of the cube to be a square, but it's not. That diagonal slice of the cube is a rectangle, right? If you actually think about this slice here and draw it out like this, the vector is in that plane like so. I mean, this here is A, this is B. This angle is not 45 degrees because this is the square root of what? 2. Yeah, this is the square root of 2, and this is 1. It's not a square. It's a rectangle. And that's why it's not 45 degrees. And you're like, that's right, and I don't need vectors to figure that out. That's true. You don't need vectors to figure that out. But it's sure nice to figure it out with vectors, isn't it? Because with vectors, it doesn't matter whether or not you can visualize that or not. If you take command of the coordinates and you write the vectors carefully, you can calculate the angle between the vectors, whether or not you really understand how to look at like cross sections and things. It gives you a way around some geometry which may be beyond you for just personal reasons. We all have different geometric, skill sets. And I think part of that is just intrinsic to who you are. I had a student who wrote some paper on the concurrency of 5 lines, and he has like circle, and there's these lines, and and there was a professor here who taught geometry who understood what he was doing, and it was good. It wasn't just some crackpot or anything, but I had no earthly idea because I don't have that gift. I can't see those kinds of classical, geometry things. With vectors, I don't need to see some of those things though, because I can use algebra to calculate the angle. That's the wonderful thing about that boxed equation, is it has traded a question of geometry for a question of algebra. We can all do algebra. Some of us can do geometry, right? Let me restate that. You will all learn to do algebra. Okay. So one of you said last class, and I do endorse your message, that a vector is a magnitude in a direction, right? And that's a good thing to say. But let's put some teeth into that slogan. Let's actually give you algebra to back it up, right? So a lot of these, everything I've been writing on this board, like parts of it are very, this is not the way I would typically write it later in the course, because I'm about to show you a notation which will simplify our life greatly, right? I've already been using part of this notation when I wrote x hat, y hat, and z hat. If we put a hat on something, that means it has length 1. So if you had a society like this, it would be like anytime you saw a person with a hat, you knew they were 5 foot tall, exactly, right? Like whatever height you are, that would be it. And you saw somebody else wearing a hat, you would know, even if they were sitting down, if they stood up, they would just match. That's how it would be. That's how it is for us. If you put a hat on it, it has length 1. Game over. End of story. That is the rule. All right? So we should talk about that. How do you find a unit vector, right? How do you find a vector of length 1 in the direction of a given vector? This is a very important concept. It's simple, but it's also important. Don't let it slip past you. So unit vectors. So if a vector is not equal to 0, then what we'll say is the magnitude of A is equal to A. Actually, this is not a conditional. Sorry. Notation. This is not. This is in no way connected to whether or not the vector is 0. And that's a silly thing for me to say. Well, this is our notation. This is a lot to write. You notice I've been careful not to write A without a vector anywhere. We write vectors on vectors in this class. If you take another class past this with me, you'll see me writing vectors without vector signs. But for this class, there's a certain legalism which we insist on. You write vectors on vectors, all right? Except when we don't. Okay, so, no, we will almost always do it. So there it is. That's the notation. The magnitude of A vector, we just write A. And so if you write something for me, like A is equal to A, like if I see that on someone's final, I really want to fail them. I mean, if you learn nothing else from this course, learn that there's a difference between a vector and a scalar. They're radically different objects. You're like, but I'm a one-dimensional being. How dare you? Fine. If you're one-dimensional, I'll let it slide. But none of you are, so. All right. Even in one dimension, the magnitude should be positive. So, all right. So that's the notation, and then definition. If A is not equal to 0, then A hat is equal to 1 over A times A. So to find a unit vector in the direction of A, we simply rescale the vector by the reciprocal of the length of the vector. So if you have a vector of length 3, divide by 3. Then you'll have a vector of length 1. If I have a vector of length 1/2, I divide by 1/2, which is multiplying by 2. I get a vector of length 1. It's inescapable. This vector has length 1. Let me prove it for you. Length of A hat is equal to what? Length of 1 over A times A vector. What did we just learn about the length of the vector function? We can pull out the absolute value of the scalar multiplying, right? But this is a positive scalar, so that's just 1 over A times the length of A. By the way, you see why it's so important to have the double bar notation? How would you communicate what we're doing right now if the only notation you had was leave the vector off of it? Oh, that would be hard. Okay, so 1 over A. Oh, but these cancel because A is not 0, right? We assume that. And of course we get 1. And now I can make precise the claim of the gentleman in the last class that a vector is a magnitude and a direction. Because the formula, it's almost right here, right? A is equal to A times A hat. A without the vector, just plain A, is the magnitude. A hat is the direction. Simple as that. It's a wonderful notation. It's really wonderful. Now, you're like, but, and so I will try to be consistent in my language in here. If I'm talking about a direction vector, I probably mean a unit vector. Some people are not insistent that the direction vector has to be a unit vector. If you do that, then this is not a unique thing, right? If your direction vector didn't have unit length, then some of the magnitudes hiding in the direction vector somehow it would be not as useful a description. So that's why we want unit length, so that all of the magnitude is completely captured in the coefficient, which I've labeled A here. So some fun games you can play with this. I can give you a vector, and then I can say stuff like, okay, so find another vector of length 7 in the same direction. So you guys, give me a vector. How about three-dimensional vector? 3, 4, 5? Oh, 2, 4, 5, okay. So let's say A equals to 2, 4, 5. Let's find a vector B of length 7 in same direction as A. There are kind of two approaches to this. Let me show you how a mathematician would probably approach it. Something like this. You'd say, oh, well, if they're in the same direction, that means I can write an equation like A is equal to some constant K times B, right? Or maybe, right, something like that. So, and let's say I need to make up some variables. I don't know what B is, right? So I could say that's, oh, that's still not the right way to say it. I'm sorry. That's not how a mathematician would do it. I gotta find a mathematician to tell me. I don't know. Let's see here. Who's a mathematician here? Somebody tell me how to do this without unit vectors. How about this? B, this is a general strategy. Make up a name for what you don't know, ABC, right? And we know that that has to be like some multiple K times A. I don't know ABC and I don't know K, but I do know that B is equal to 7, right? The length of B is 7. What else? How do I calculate the length? How is length of B related to ABC? Yeah, exactly. So 49 is A squared plus B squared plus C squared. I don't know. I like to think about the square of vector length. It's often easier. Because I'm just going to square that square root eventually. And what else do we have? We have this equation. We also have what? We have A is equal to 2K, right? We've got B is equal to 4K. And we've got C is equal to 5K. Because, why do we have that? Well, this is a vector equation, right? Vector equations are kind of sneaky. It looks like one equation, but it's actually 3, right? In order for these two things to be equal, they have to match up. Remember last time we defined vectors to be oh, maybe I didn't. Did I tell you how vector equality works? I don't think I did. Oh my goodness, shame on me. When are two vectors equal? Yeah, each and every component has to match up. So like the x component, the y component, and the z component here all have to match. So that's how I got A is equal to 2K, B is equal to 4K, and C is equal to 5K, right? If you thought about this for 10 minutes or something, everybody should come to this eventually, right? And then, so of course, you can plug those back up in here, and what do you get? Four plus 16 plus what? 25? Oh, 40, 45? All right, so apparently K is equal to what? Plus or minus the square root of 49 over 45. And we can choose the plus because we said the same direction. So there you go. B is equal to square root of 49 over 45 times 245. And by the way, I think that's a perfectly good format for an answer like this. It doesn't really show me, I mean, if I ask you to not leave a scalar out front, that's one thing. But if I don't say otherwise, that's a perfectly acceptable format for the answer. I don't think bringing the scalar inside and writing it 3 times really gains much of anything. All right? Like some of you are like, square root of 49 is 7. Fix it. Fix it. Okay. 45 is reducible to 9 times. What are you doing? It's not simplified. All right, fine, whatever. I'm going to ignore you. Haha. Now, this is the wrong way to solve this problem. Because geometrically, there's a much easier way. Yeah, how would you do it? I thought I saw. No? Okay, so how about this? Here's how I would picture it. Here's A, right? And then there's B. Actually, I don't know which one's longer. I said find B of length 7. I don't know, is B longer than A? What's the length of A? 6.7 meters. Oh, wow.
I was trying to do it my own way and got tangled in my stop.
They're almost the same. That's kind of funny. Yeah, oh, yeah, right. The scale factor is really close to 1, isn't it? Yeah. Right. That's true. I mean, we can see that from what we did, but would you have known that a priori? I mean, maybe before the fact? I mean, I think you're making an observation. I think you're making an observation about the solution, which I totally agree with. Ah, yeah. Well, let me just. I'm not. The way I think about this usually, guys. Whoop, is there a red vector? Vector. Gosh. Yes, thank you. Throw it thing. Thank you. So here's what I do. I say, okay, geometrically, what I think about is A has like there's a little A hat right here, right? So to get a vector in the same direction as A of length 7, I just need 7 of those. Ka-chunk, 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 ka-chunk. So the answer is B is equal to 7 A hat. Here's how you use unit vectors to solve problems that would otherwise take effort. That's a geometric solution, right? I use geometry to scoot past this algebra right here. And well, of course it's not done. I mean, you have to calculate A hat, right? What's A hat? 7 over the square root of 45, I guess. Yeah. And then 245. Of course, we agree, but I think you can see what I wrote in red is way, way easier. So, I mean, it's kind of a typical test question. Here's a vector. Find a vector of this in the same direction of length whatever. The simplest way to solve the problem is find a unit vector and multiply by the magnitude you want. Yes, sir?
How did you find the A hat?
Definition. I take the vector and I divide by its length. Now, I happen to see this 45 over here, so I knew that the length was 45. Yeah. But to actually find that, A is equal to the square root of 2 squared plus 4 squared plus 5 squared, which is the square root of 45. Yeah. So that's how. Yes, sir. Which one? This? No, A hat. That has to be A hat. Not the magnitude. No. If this was so, it's a good. Actually, I'm so glad you asked that. If I put 7A here, just think about it. You know you're wrong because I would have a vector equals 7 times a number. And to quote my community college professor, that dog won't hunt. Okay, it's not going to work. All right. Okay, how much time do I have left in here, guys? I forgot. It's still 5? Oh, wow. So they took away time at the beginning, but they gave us time at the end. It used to be till 4:50. No, it was till 4:55 before, wasn't it? You guys aren't freshmen. You were here last year. Don't pretend like you don't know what I'm talking about. Oh, you are. It's always been an hour 50 minutes. I know. The end time. I think end time for Tuesday, Thursday used to be 4:50, right? Yeah, I know. I'm still. I'll try to be done by 5:15. Just let me just grab these. All right. What is the relation between dot products and the components of a vector is the next question that I want to ask. But another thing there's something I need to define here before I forget. That's the notion of orthogonal vectors. What does it mean for vectors to be orthogonal? Well, the angle between vectors we defined, right? It's defined by the dot product of that box. Oh, man. The formula I had boxed over there. Oh, there's something else I keep forgetting. N equals 2 is special, right? If I have a vector, I knew there was something I'm forgetting. If I have a vector that's like this, right? So let's say v1, v2. In 2 dimensions, we can also describe its magnitude and direction in a different way, right? Yes, I could write that this is equal to v times v hat. Still fine, right? Where the magnitude is the square root of v1 squared plus v2 squared, right? That's still good. But there's another way to describe its direction in 2 dimensions. What is that? Yeah. Yeah, polar coordinates, right? The angle. So we could define it in terms of the standard angle theta. And so that's another thing that's commonly done. You can ask, for a 2-dimensional problem, what's the magnitude and the standard angle? And I do ask that sometimes on tests and things. It's important that you guys know about that. And there's a lot of traps there, right? Because polar coordinates are a little bit tricky because there's no one inverse trig function which is defined in all 4 quadrants, right? Inverse tangent gives you the right angles between quadrants 1 and 4. I think inverse sine works also in quadrants 1 and 4. Inverse cosine is good for quadrants 1 and 2. Nobody's good for quadrant 3 unless you do shifting, right? Like, for example, if I have v is equal to -1, -1, well, the magnitude is square root of 2, right? What's the angle? See, if you think that the tangent of theta is equal to -1 over -1, I mean, you'd be wrong, but that would be 1. So theta would be inverse tangent of 1, which is, by the way, 45 degrees, or pi over 4, which is obviously wrong, right? It's that plus what? Plus 180, right? So this is not entirely truthful. In fact, theta is equal to 180 degrees plus 45 degrees, right? So you still, so 225. So that's another way I could describe the direction of a 2-dimensional vector, right? I could use a magnitude and a standard angle. In fact, I can do more. Sine and cosine, there's all kinds of really nice formulas connecting all these things. So this right here, let me just say that's v1, right? Sometimes I would call it vx. This over here would be v2. Well, that's equal to what? That's equal to, this is v. So that's v cosine theta, right? This is v sine theta. I drew the picture in quadrant 1, but sine and cosine are so defined as to make this formulas extend to quadrants 2, 3, and 4. Sine and cosine switch from positive to negative precisely so that these equations still make sense in the other quadrants. And so, with that in mind, we have v is equal to v cosine theta, v sine theta. But you can factor out the magnitude, right? So you get v cosine theta, sine theta. Well, compare. Compare. Here's your v hat. Here's your v hat. In other words, there's a direct relation between v hat and the standard angle, and here it is. So if I want to create a unit vector in the theta direction, I can use this boxed formula. Simple as that, right? So if somebody says, create a vector which is at standard angle 300 degrees of length 7, how would I do it? Personally, here's how I do it. All right, so length 7, 300 degrees. I'm ignoring special angles and all kinds of stuff because I've got a calculator. Make it 307 degrees if you're a math major and what I'm doing right now is bothering you for some reason. Okay. Odds are against it, though. And there it is. That's a vector of length 7 that points at the 300-degree angle. All right. Now that I've got that out of my system, I do assume that you studied polar coordinates in calculus 2. I'm not going to go and do that all again here. We will pick it up as we need it. All right? I mean, we'll talk more about polar coordinates when we do integration a little bit later in this course, right? So, although I guess you're probably happy that you're taking a little break from integration, huh? I think that's why a lot of people think calculus 3 is easier than calculus 2. It's like, oh, this integration, these convergence, divergence tests. And then all of a sudden you go to this course and you're like, the length of a vector is square root of 3. This isn't calculus, this is algebra, right? We haven't done any calculus yet this semester, well, except the part I was digressing. All right, definition. A is perpendicular to B if A dot B is equal to 0. Now, I say perpendicular, but you could also say orthogonal. All right? And this term orthogonal is generally used for the notion of perpendicularity, if that's a word, in more abstract context. Very important idea. Do you know some examples of orthogonal vectors? We saw some at the start of this lecture, right? Xhat, yhat, zhat. Those are orthogonal. What's the angle between orthogonal vectors, yeah? Right. Now, how do you know that? Geometry, right? But this formula, right? AB cosine of theta is equal to 0. How can this be 0? There are some choices, right? Either A or B is 0. That's another possibility. The 0 vector is perpendicular to everything. Kind of a stupid case. But otherwise, if A and B are non-zero, it must be that the cosine is 0. When is cosine 0? Pi over 2. That's right, 90 degrees. So now, one of your homework problems, one of you guys are puzzled about, how do you find the distance to the line, right? Now we're getting closer to that. Because if you think about it, here's just a hint on one of your homework problems. Throw it out there. If I've got a line, which, by the way, I haven't really explained to you how to properly handle mathematically. We will get to that soon, before the week is done. You know, if I want to find the distance to this point here, to the line, what I want is the closest distance by definition, right? So really what you're looking for then is some kind of vector like that, right? Or like the other way. Let's say the other way, like this, right? And you want that to be what? You want that to be perpendicular to the vector which lies in the direction of the line. So if you can find the vector which is perpendicular to the tangent vector to the line, then the length of that perpendicular vector is the distance from the point to the line. Okay, but we'll get there later this week. We still are developing the toolkit we need to solve that problem properly. Just to look ahead. All right, so projections. Projections. Let's talk about projections. So what is a projection? Here, watch. I projected the marker onto the floor, right? I set its z coordinate to 0. See that?